Hi everyone, so today we are going to continue with the book Designing Data-Intensive Applications, and we are going to look at Chapter 2, Data Models and Query Languages. So there are two dominant approaches to data modeling, the relational data model and the document data model. So in a relational data model, data is organized into tables or relations, and each relation is an unordered collection of tuples. This is the dominant approach used in many databases such as MySQL or Postgres. And from a data model perspective, it has a lot of advantages, but also a few disadvantages. And a couple of them are the object relational mismatch. So when you work in a programming language, you need to work with objects, and those objects need some attributes, and those objects are constructed from the data in the database. But there needs a translation layer between the relations or tables in the database to the object in the programming language. And that's where you need to have an additional layer of translation called an ORM to be used to construct the objects. So that's a little bit of an impedance mismatch between what is in the database and what is in the memory. The other problem with relational model is that it requires joins of multiple tables, or it requires multiple queries if you don't want to join the tables in one-to-many relationships. So to illustrate this point, let's look at a resume application where the data is normalized. So we have a users table, and by normalization, I mean the data is laid out into tables so that there is no duplication of the same information. So here we have a users table. So that's the user for which we are building the resume. And then that user table contains the information of the user, for example, name and summary, and then references to region, industry, and photo. And then there is a positions table, which contains positions held by different users. And if we want to collect their resume, we will join the users table with the positions table, their education from education table, and their contact information from contact info table. Now, we could either join these tables to get user 251's information, or we could read user 251 and then create multiple queries to get their information about positions and educations and so on. So to alleviate or sort of fix these problems of one-to-many relationships, where one user has a relationship to multiple tables, we can look at document data model. So in document model, data is stored in documents. So if you have user 251, they have some attributes, and then their positions are all sort of encompassed in the same document. So they might have a couple of positions held at a few organizations, and then their education at a couple of educational institutions. And all of it is in a single JSON document or some other format. And one of these document is one record referenced by this user ID. So this is great when there are no or fewer relations between documents. So if all you care about is a single document, a single person in your application, then this is really great. The problem with the document data model is that it doesn't represent many-to-one relationships very well. So in order to do many-to-one relationships, you would have to duplicate data. So for example, if this organization itself had a few attributes, what you would do is either duplicate it in every document which references this organization, or you would have to create additional documents for each organization. And then you would end up with the same sort of relational model. So here is another, the same example illustrated graphically. So we have user 251 and user 467. So if they are separate documents, then all is good. But if we put in organizations and school information, in that case, multiple users might have to reference the same school or organization. And so one approach is to duplicate the school information in each of these documents. The second one is to do joins with these other documents, and joins are not natively supported in the document model. So that's where the relational model becomes more appropriate for many-to-many and many-to-one relationships. So leaving the fault tolerance and concurrency and consistency and all those things for later, if we have to just decide based on the data model, which one would you want to use, the relational or the document model? So there are a few things to consider. The first one is which one does result in simpler application code. So if you have a problem where the data has a tree structure, such as the resume, then the document model is the ideal choice, because relational model will shred the data into many tables, and then you would have to do joins to collect that tree. But if you have many-to-many relationships, then relational data model is better, because document model requires denormalizing or basically duplicating data in each of the document, and that will cause some overhead. The second attribute that you could sort of use to decide on the data model is the schema flexibility. So the document model allows you to be more flexible. So if you have the document model allows you to have schema on read. So when a client is reading the document, they could choose which attributes they want to read from each of the document. And this is really useful if you don't have control over what is being written to the database. So if an external application writes to the database, and you have only control over the client code or the code that interacts with the reading side of things, then schema on read is what you need. On the other hand, if you want to enforce structure on what is being written to your database, then the relational database is the way to go, because it requires you to only write data for which the schema has already been defined. And if you need changes to be there, if you want to do some changes to the schema, then you would have to do expensive migrations. The other attribute is data locality for queries. So in a document model, the data is stored as a single string. So everything is in one place. So you could read the whole document sequentially, and it's much faster to read sequentially from disk compared to doing multiple seeks or multiple readings from the disk. And so if you want better performance in terms of data locality, then the document database is what you would choose. Having said all these things and having looked at all these attributes, in recent years, document and relational databases have converged. So a lot of the document models would support joins, and a lot of the relational databases support JSON and document objects as well. So there is the boundary between the two have blurred quite a bit in the recent years. So those were about data models. Now let's talk about query languages. And most of the query languages in databases or data applications these days is declarative languages, because declarative languages abstracts away the implementation from the functionality, and that allows databases to really optimize under the hood without changing the interface. So here is some imperative code in one of the languages, JavaScripts here, where we have an animals table or array, and we want to extract sharks from it. So we define a sharks array and iterate over all the animals and check if the family is sharks. We add it to the sharks array and return it. So that's the imperative way to do it. In a declarative way, we would use for example, in SQL, we would use a statement like this: select star from animals where family is equal to sharks. And in this case, there's a stark difference between the two. The result is the same, but in this case, we are expecting that the sharks will have the same order as its order in the animals array. So the code cannot be optimized, or you can't assume that the order in sharks is unimportant to the client, because we have exposed it through this imperative code. Whereas in here, there is no guarantee on, given this statement, there is no guarantee that the records that are returned from this declarative statement would be in any order. So we could really optimize everything under the hood as long as we return animals that are from the sharks family. We should be good. So we looked at data models, relational model, and document model, and we looked at the query languages for them. Now, if you have no relations between records, you would use document model. If you have many-to-many relations, relational model is what you would go for. But if the data is really interconnected, for example, social networks where there are people and there are friendships and everyone is connected to a lot of other people, then in that case, you want to use a graph model. And a graph model consists of vertices and edges. So vertices could be, if it is a social graph, it would be people, and edges would be friendships between them. The vertices could be web pages, and the edges could be the links between them, and so on. And graph models also accommodate heterogeneous data. So the vertices could be a combination of people, location, events, comments, etc. So there are two types of graph databases or graph models. One is the property graphs, and the property graphs is just a set of vertices and a set of edges. And a vertex is defined by a few attributes. One is its identifier, a set of outgoing edges, and a set of incoming edges, and a collection of properties, which is basically key value pairs. And edges have similar structure. It has an identifier. It has an vertex at which the edge starts, and a vertex at which the edge ends. It has a label to describe the kind of relationship between the two vertices, and it has a collection of properties. So if you want to declare or sort of create a property graph in SQL, here is how we would do it. So we will create a table vertices with vertex ID and some JSON properties. And then we will have edges with tail vertex and head vertex, a label, and some properties. And we can create a couple of indices for the tail vertex and head vertex to be able to efficiently traverse forward in the graph and backward from a given vertex. So this is if we want to use relational schema for or relational language like SQL for graph databases. But graph databases have evolved, and there are a lot of specialized languages for graphs, and one of them is Cypher. So if we want to, let's say, create this graph using Cypher, so we have a few nodes representing, or vertices representing locations within locations. So these are the edges, which represents the within relationship. And we have a couple of persons, and edges that are either born in or lives in. Now, if you want to create this graph in Cypher, it's really easy. You just specify a few of the attributes. So you say create, you provide a label here, North America, location, and then a property JSON or key value pair. So here we are providing a name, North America, and type continent. So this will create this vertex. Similarly, we create a few more vertices, and then if you want to declare some edges, we would say Lucy, this is the vertex name, and born in is the edge between them. So and then we have this next vertex. So given this, we can define, this is just defining this part of the graph, but similar queries, similar syntax could be used to create the whole graph. Now, if you want to do some queries like find the names of all people who immigrated from the United States to Europe, so this means everyone who was born in United States, so born in United States but lives in some other place like here, Europe. So how would we do it in Cypher? We will just run this query. So we have a vertex of type person, and we have this edge, so the outgoing edge from that vertex, which we named as person. If the outgoing edge is born in, and then it goes to some other vertex, we can name it here, but we just chose not to give it any name because it's not going to be used later on in this query. And then we traverse 0 or more within edges until we reach a vertex that has type US location, and its name property is United States. So that's the born in so this will match with everyone who was born in the USA. And then the next filtering, or whoever matches this first line would be matched against the second line, which is also looking at a person vertex that lives in within 0 or more outgoing edges of a location named Europe. And once we match these two conditions, then we return person.name. So this is really just 4 lines of code or query in Cypher. But if you wanted to do this in SQL, it would be very complex to accomplish the same thing with SQL. It would take about 29 lines of code. The book has provide all the code in SQL. Apart from the property graph, there's another representation of graph models, which is called triple store. And it is mostly equivalent to the property graph model, but it has the structure of triplets or multiple tuples, where each triplet has a subject, a predicate, and object. So, for example, Jim and bananas are two vertices, and likes is the edge between them. So there is an equivalence between the property graph and the triple store. And one of the languages to describe triple store is SparkQL. So that's just a little bit of an overview of graph databases. So that summarizes our today's video and chapter. So we discussed relational model, which solves the problem of many-to-many relationships and stores data efficiently. But some applications don't fit the relational model really well. And for them, the document databases provides a better representation. And in document databases, data is self-contained with rare relationships with each other. And in graph databases is the other extreme of document databases. So relational models are in the middle. Document databases, no relationships. Graph databases, anything is potentially related to everything.